Hey, how's everyone doing today? We got Tiffany here. I don't see. Is there an updated email? I think we were talking about the graphics last time, and I said only include a certain amount of graphics. I was looking at the emails over here. Let me see. Get so many. Oh, this. Okay. That's. Let me mark that as red, but that's a software I use. Emailed me. If you have questions, put them in the chat right now. I'm kind of knocking out some emails, seeing things I need to read or not read. I see right there. A lot of stuff going on in the background. And visualization. There we go. Visualization 5. Let's see. Let's see what people are saying in the chat. Hey, I did yesterday evening. Let me look for that real quick. Let me look for that. Okay, let me go look here. How did I miss that? Did I click off of it? Double check, Tiffany. I see one from yesterday morning. Tiffany, make sure it's sent. The last one I have is from 9:25 yesterday morning. You might need to resend it. I don't see it. Maybe there was something issue. Maybe it went to my spam folder. Maybe it got. YouTube better not be sending things to my spam folder. I'm taking a look right here, trying to see. It's not in my deleted. I wouldn't delete it. Where's my spam folder? Do I have a spam folder? Junk email. Please tell me it didn't go like junk email. No, nothing junk email recently, which it shouldn't. Resend it because I don't see it. For the decision tree visualization, when I go to the split screen and the plot colors does not show up. Let's take a look at some. Yes, and so yeah, I should maybe remake that video. Maybe I'll do that over break. I'll remake that video. There's different ways decision trees can go. So here, let's start off talking a little about decision trees visualization. And Tiffany, double check that send. You sent it at 3:20. Can you resend it? For some reason, I don't see it. Or reply to it. Double check it was sent to B. Stevens. Sometimes people accidentally put it on the B. Stevens 2 or something, or 3. So I don't see it. And I'll take a look at it here in a moment. Let's go take a look at a decision tree and talk about what decision trees are. This is decision trees visualization number 6. So when it comes to a decision tree, we're using a lot of X's to predict one Y. So one of the big things to know right here is we have 2 types of decision trees. So a good hint for your assignment. We have decision trees that are for quantitative X's or for categorical X's. To make a decision tree, we go to Analyze, and then we go to Predictive Modeling, and we go to Partition. It's going to partition the data into groups. You can see the graphic right there. It might be a little hard to see right there. But that graphic is going to partition our data into groups, or the visualization will. And here's what we need for decision trees. We need to only use quantitative and categorical variables. So what will we not use for decision trees? I'll take a pause right here, and this is a good conceptual thing to know. What do we not put in decision trees? What do we not put in decision trees? We will put quantitative variables. We will put categorical variables. What will we not put in decision trees? Turn out some points. Reset in the MuBot. Just resent it. Awesome. I'll take a look here in a second. We will not put into decision trees identifiers. Josephine, great answer right there. We will not put into decision trees identifiers or things that act like identifiers. I think you might email me too on this. Great question. So showing up here, seeing how it works. So we will not put in things that are identifiers or things that act like identifiers. Now, what is something that acts like an identifier? Something that acts like an identifier would have lots of levels. We can kind of get an idea for what's going on. Now, someone's age is not an identifier because it's quantitative. Somebody's high school GPA is not an identifier because it's quantitative. We're only going to look at things that are identifiers, like this literally says identifier right here. So couldn't be more clear that that is an identifier. Now, it is showing that it's blue, but in truth, it could be something like none. It just deletes it. I've never done that before. It's just an identifying number for which person we're talking about. So that is not a quantitative variable. That is actually a non-variable right there. It's an identifier, excuse me. But take a look at this. What do you notice about major? What do you notice about major right here? There are 427 additional levels to major. And this is a good way to see if things might be an identifier. Go ahead and take your data set right here and then click this button and jump to see the values. Now, if something is quantitative like age, it's not an identifier. If something like high school GPA is quantitative, exactly, Alexander, right there, lots of levels. And that's what we're looking for categorical variables. I can't make that clear. This is categorical. A categorical with a lot of levels may act like an identifier because there's a lot of unique levels which wouldn't identify but almost kind of do that a little bit. So we don't want to include those. So major's one of them, and that looks to be it. For my data set, major's the only one. And when does it have a lot of levels? Let's say more than 10. Now, statisticians are going to argue about what a lot of levels are, but we'll say right here, a good way to know is if you see more than 10 levels, when you pull this down right here, this has 3 levels. Levels is how many answers there are. This has 4 levels, 4 levels. These don't have too many levels. So Alexander, how are you doing on finding the ones that have too many levels? Like this has 1, 2, 3, 4, 5 levels to the variable, 5 answers to the questions. Have you been able to find the ones that have too many levels when you look at it and you say, whoa, that's too many levels, like answers to the questions people gave? One way to do it, once again, is to click this inside of Jump and then pull it down so you can see. Now, once again, do not take things like quantitative variables, like this is expected salary. That is not going to be an identifier or act like an identifier. So this is not an identifier, but it kind of acts like one because there's so many unique levels. Like we have right here, the person who is doing public relations, there might not be many people doing that, or maybe there is, I don't know. Or the person doing ag business. Now, it's probably agricultural business or exploratory. All of these different answers right here might identify one individual, like pre-pharmacy. Maybe not a lot of people doing that. I'm trying to find something really unique right here. HRT. Don't know what that is. Human resource training, is that what it is? I don't know. So yeah, hey, business analytics. So anyways, we want to not include these. So let's go back to the partition model, and I'll show where that's at again. Analyze, and go over here to predictive modeling and go to partition. And this is how we build a decision tree. Yo, good to see you here, Adam. And so when we build this decision tree, here's what I do. I go ahead and I click Control or Command A. Now I hold Control or Command and I deselect what I don't want. I do not want an identifier and I do not want things that act like identifiers. I'm holding Control right now, which is letting me deselect them. On a Mac, hold Command. Then I'm going to take everything and put it into the X. We will pick our Y here in a moment, but I'm taking all of these and putting it into the X. And now I might want to explain a variable like, let's say, somebody's high school GPA. I'm going to click it one time. An important thing to do, click it one time. If you click and drag, you'll do this. You want to click the variable one time and let go, and then drag the variable up to the Y. Not a big. I like boneless wings, so I'm weird. Because a lot of people like. I used to like Buffalo Wild Wings on the Strip, and they had some good deals, and then they went away. But they used to have like 20-cent wing like Tuesdays or something. Ooh, I've been buying a lot. This is visualization number 6 right here. We've got a quantitative Y variable, and how many X's do we have right here? How many X's do we have? What is the point of a decision tree? One Y, lots of X's, and the Y can be quantitative or categorical, and the X's can be quantitative or categorical. There was 2013 or so, it went away. 2012 maybe? Gosh, okay, it's been a decade since we had a B-dubs on the Strip. It's where Uptown is now. So that was where B-dubs was. And then it became like a TGI Fridays, or it came out Applebee's or something. Back in the day. Here's our visualization. And we're looking at the different average GPAs for groups. Right now, everybody's all together. What does this 482 mean right here? Let's interpret this and see what this means. What does that 482 mean? Just take a moment and think, what does that 482 mean? What is that telling you about this? What does that 482 mean? 482? What? What does that mean? 482. If you can understand what... That's the sample size. Josephine, great job right there. Some 100 points in the chat. That's the sample size. We have 482 observations right now, and the mean of these 482 total observations is a GPA of 3.81, and the standard deviation, which is the variation within the group, or standard deviation is a measure of spread, is 0.4. Now, when I go to split, here's what the decision tree does, is it looks through every variable and finds the best possible variable to split people into groups to explain high school GPA. And the number one variable is, wait. Oh, do I have it? Oh, wait. Oh, I was not prepared for this. Nope. I was looking for a drum roll. Don't I have a drum roll on here? Can't find it. Number one variable is age. Age is the number one. That's not a drum roll. The number one variable is somebody's age. Look here. These are the water people, the people who have an age of less than 20. This is the question number. That's just Q2. Was question 2. People who have an age less than 20, the 280 individuals who qualify for this, had a GPA on average of 3.9 and had a standard deviation, which is just variation. Check out. We'll be checking that out later here, Corlin. Great question. And then individuals who had an age greater than or equal to 20 would have, there was 202 of those individuals, and they had a lower GPA. So notice here that younger people generally have higher GPAs. Maybe it's grade inflation or something like that. Who knows? It's what the numbers show. Now, when we split again, it's going to look through every single variable and tell us the best variable to explain GPA. The next best variable here is going to be if someone's in the honors program. So I want you to, and this is hints for your visualization, right now, tell me about the people with the highest GPA. They are people who have what for age, and then they have what for what else. Tell me about the people with the highest average GPA. These 47 people, tell me about them a little bit. Just talk to me about them like this is your visualization. And I want you to be like, well, the people who have the highest GPA would be individuals who are this and this. So just talk to me about these individuals right here. Talk to me about, just explain to me what's going on with these individuals. The individuals with the highest GPAs would be the people who are what? The people with the highest GPAs would be people, and follow the tree down. Just be like, boop, 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 boop. Under 20 and are in the honors program. And that makes sense. Like younger people in the honors program were the people with the highest GPAs. And then I'm going to do something special. I'm going to make my tree symmetric. If you have to split it 3 times, this is going to split the tree. I'm choosing to split it here because I like symmetric trees. They're easier to take pictures of. And we're going to split it right here to make a symmetric tree. And it actually split on honors program again. So now, and actually this is, be careful, I've created a conundrum for myself. These 5 people right here actually have the highest GPA. Does that make sense, Alexander? Do you see these 5 people actually have the highest GPA on average? It's a very small group, but it's split on honors program right here. We could split again and see what it does. You might not have to split this many times. And now it does it on relationship. And these are actually the lowest GPAs. But does that make sense? We're looking at the mean for each group. Oh, it's making my tree go all crazy. So let's split here again. This is a little bit like clustering. This is partition models, decision trees. A little bit like clustering, though, but this is more of a predictive model where clustering is descriptive models. So now the people with the highest GPAs, watch out, are going to be people in the honors program who are 20 or older. They had an average GPA of 4.22 for these 5 individuals. Does that make sense as I say it right here? These 5 individuals are in the honors program, and they have an age of 20 or greater, equal to 20 or greater, and they had the highest GPA of 4.22 on average. The people with the lowest GPAs were the people who were older, who were not in the honors program, who had an average of 3.669 as their GPA. There were 197 people in this group. Now, we can actually look at all these groups with something called the LEAF report. The LEAF report can be found under the red arrow. And the LEAF report is going to summarize all this. You probably need a picture of the LEAF report in your visualization. So take a look. These are the questions you would have to go through for each group, and it's pretty easy to see this is the highest mean. So these people are people with an age greater than or equal to 20, and they are in the honors program, yes. Is this making sense, Alexander, how to read the LEAF report? It just has the questions that were asked. Someone has an age greater than or equal to 20. That was the first question. And they're in the honors program. These Qs are just the number of questions asked. Q17 just represents question 17 on the survey. So the group with the lowest GPA, once again, was people who have an age greater than or equal to 20. You can see it right here. And then they are in the honors program, no. So they are not in the honors program. Now, one thing I want to point out right here, and it's so valuable to know this for your LEAF report, is the following. When you're looking at your LEAF report, the LEAF report will always go in this order, and let's make this very clear. We're almost doing a mini lecture on this topic. When you look at your LEAF report, here's how the LEAF report looks. The following is LEAF 1, LEAF 2, LEAF 3, LEAF 4. And up here you have LEAF 1, LEAF 2, LEAF 3, LEAF 4. From left to right, you will see the leaves. So is this making sense right here? When you look at this, if I were to highlight the data right here, that is LEAF number 3. Those are the 233 people with a GPA on average of 3.86 who are not in the honors program and who have an age less than 20, which you do see down here in this information. So you would just follow the path down. If you had to follow down to it, you would follow down to this leaf right here to ask the questions for leaf 3. Understanding how to read this output is the key for the assignments to make sure you kind of go through and follow through the tree to say, okay, these people are less than 20 in age. They are not in the honors program. There's 233 of them, and their average GPA was 3.867. The last thing that you probably need in your report is going to be a split history. The split history is showing you the increase in the R squared. So when you're looking at this right here, I did do some craziness. My tree went back and forth a little bit. Yours shouldn't. But this is showing how much the R squared increases or decreases. You could always do this sort of thing right here. Yours won't have the craziness. But what happens as you split the tree? As you split the tree, good conceptual concept, ignore my craziness right there. As you split the tree, what will R squared do? As you split the tree, R squared will do what? Because the X's are going to explain more variation. So as you split the tree, the R squared is going to do what? As you split the tree, the R squared is going to do what? As you split the tree, the R squared, and here we can view it visually. As you split the tree, I always hate that it does that. Let me remove those things because it's going to keep going down to the bottom and update that output. Leaf report gone. Include these. Split history gone. As you split the tree, the R squared will do what? And just take a look. The R squared will do what? It'll increase. Because what do the X's do? X's do what in models? Now, you don't want to do this. This is a bad idea. This is overfitting for 474. This is what we call overfitting a model. Yeah! Let's do it. Daniel, we can do that next right here. I'm going to answer Kate Corlin's question next. And Daniel, you bet. You got the next question on here. What happens as you include more X's? Good question, Daniel, also for 320. If you include more X's in your model, what's going to happen to R squared, which is the percent of variation explained if you add more X's? Adding more X's into a model will increase the R squared because what are the X's doing? Think conceptually right here. What do X's like to do? X's like to do this. X's, I'm losing it. X's like to what? By adding in more variables. This is a horrible idea. This tree is ridiculous. This tree right here is insanity. But what do the X's like to do? And thus we see the R squared go up. X's like to explain. Great job, Alexander, right there. So when you increase the X's in the model, which is a horrible idea, we could look at the split history right here. You wouldn't want to do this. The split history down here on the very, very bottom is going to show that as you increase it, I changed the graph so it's looking all crazy like. This is just a bad idea. The R squared will keep going up. We call this overfitting. You don't want to do this. You probably only want to put probably you'd stop about here, maybe 6 splits max. The assignment is going to tell you how many splits to do. But the split history shows you the R squared over time, and you can see the R squared kept going up to where we hit some parameters we couldn't change, like the minimum leaves, min size of the number of observations in the leaf is one way to stop the tree. Like the tree is smart enough to stop, but this is completely overfit now. Don't worry about overfitting. But does that make sense, Alexander? And I think Josephine were asking about this. Oh, God, look at that. It's all craziness right here. We'll go to leaf report. It's craziness. This is a bad tree. Make into data table. So, yeah. What was the highest group? Sort. Do not do this. Descending. The highest group right here are individuals who are less than 20, are not in the honors program, are single, dating, or exclusive, and that's the highest group right there, but there's only 7 individuals. We really oversplit this tree. You wouldn't want to do that. You want to look at your split history and kind of tell when it levels off, but we do have better ways in upper level statistics of dealing with this. Oh, no, I'm just Brian Stevens. No professor yet, no PhD. But thank you so much, Alexander. Thank you for positivity right there. Let's handle Corlin's question right here. Here, I'm going to put up a quick thing right here. And then Daniel, we'll be working on your question next. Thank you so much. And then it's open questions. So throw those questions in. Let's talk about some residuals. And when we're talking about residuals right here, what is the formula for the residuals? Let's go check it out. Who knows the formula for residuals that I like to write? Here's the actual formula for residuals. So we got the actual formula for residuals on the screen, but I don't like to say that. When Brian says the residual formula, how does he say it a lot of times? So residuals are E. Yeah, I'll look at that next. Tiffany, you're right. You'll look at that next. You got it. I'll look at that next. I'll give some comments here. So residuals are E, but I don't like to say that the residual is equal to the actual minus the predicted, which is from the model. You can see the model gives you y hats. So what is a good way to remember? So what do I usually write down here on the bottom? This dude, like, practice right here. See if you remember how we write out the formula for residuals. That residual is equal to what? I'll give it 30 seconds before I get the answer. So what do we do for the residual? If the easy way to remember it is the residual wrap. Residual equals what? Like, residual equals to what? Like, the y, sometimes called the observed. I don't call it the observed, but you'll see in the notes sometimes called the observed value. It's what we see, that y is at 20. That's where it hits the y-axis. The y-axis is 20 right there. And then we have right here the predicted. So that's the predicted value from the line. Yes, Alexander, great job right there. I like to call it actual. Alexander worth another 100 points right there. Good practice. It is the observed. And so what you observe, I like to call it actual, because then I can say residual equals actual minus predicted and say residual wrap. But Alexander, you're right there. Residual equals, you can call it observed. So let me rope. But that's the observed value. This is what we observe for it right there. So you can call it observed or actual. I like to call it actual. It's like what is the actual value of y? And all of these are synonymous right here, as in this is the actual value, this is the predicted value, and the E is the residual. So good practice right there. And so this will tell you that if the residual is positive, well, then the actual is going to be greater than the predicted. And yeah, we can go right here. The predicted is on the line, and negative residuals would have an actual lower. So that's the actual value of y would be over here. And the residual is going to be this distance it is below. So that might have a residual of something like E equal to -8. Just going by perspective right here. No, that'd be wrong. So what is the actual value of y? 50-point question on the line right here. What is the actual value of y right here? Who can figure out? Decent test question. Visual helps out a ton seeing this. You know that... Oh, we don't know the predicted. Ooh, can't answer the question yet. Here, this makes it easy. That's close enough. Oh, wait, not negative. So what is the actual value of y right here? So it's predicted to be 18. The residual is -8. So just practicing, like, conceptually, if it's predicted to be 18 and the residual is -8, and you can see visually where it's at. So what would be the actual value of y? This is a good test question right here. The observed value of y or the actual value of y would be what? A point is predicted to have a value of 18 from the line. So we see up there. And the point actually, it has a residual. Great job, Alexander. So all you're doing is just saying, well, then it's 8 below the line. That's what the residual tells you. So the actual value of y right here has to be equal to 10, because the distance that it is below the line right here, the residual right here is the distance is below the line. So it's 8 below the line, and that's got it. Great job, Daniel, and everything. Good practice for 320, knowing how to do those residuals. And you know what's so great? Just want to mention this. In 320, if we have a model and we want to get those residuals, there's all the residuals. And to kind of, here, I'm going to throw Daniel a quick thing real quick. Daniel was asking about, I cannot find how to get the slope or the SSE for an R. So if you want the slope, I'm going to come back, Daniel, and review this more in a moment. Slope's going to be in the summary. It's quick hints right here. Slope's going to be in the summary. And the ANOVA is going to have the sums of squared error. And it's not capitalized, is it? Here's where to find the slope is going to be in the summary. So here's all your slope information, like the estimate of the slope, the standard error of the slope, the standardized value of the slope, and we divide it by the uncertainty, the p-value of the slope for the significance of the slope. And then down here, we have what our model explains, sums of squares, what our model does not explain. And if you add these together, you'd get the total. More on that in a moment. I'm going to take a look at Tiffany's email, and then we'll come back right here. So we're going to review that more in depth. Let's take a look here. So Tiffany, I'll give you some comments. I might reply more in depth. But here we go. Can you take a look and tell me if it's good or not? Yes, let's see. I'll give you some tips. You ready? Okay, visually, there's got the graphics. Oh, I like it. Condition, yep. Yeah, and the positive direction wouldn't matter for the line. Tiffany, you might want to say there's a tiny bit of a bend, but it looks mostly okay. If the graders take off points, tell me. It's mostly linear. Dropping hints right there. You might say there's a tiny bit of a bend. Like, let me see. Yeah, you say mostly go through. Yeah, you might say there's a tiny bit of a bend. If the graders take out points, it's not the biggest problem. Let's see, 2 carats. Yeah, it's a bit of an outlier. I'd agree. The graders should be a little bit nice on this. Yeah, and the biggest condition is the last one. There we go. And then also diamond can't have negative carats. Yep. Yeah, this looks excellent. And I hope Terry tells them to be a little bit nice on those conditions right here. Maybe I'll send out a thing to my graders. Tiffany, tell me if your grade comes back less than perfect. I think that's excellent, Tiffany. Great job. Tell me if you get less than 10 out of 10. So I just replied to it right there. Thank you, Tiffany. Did you see, Tiffany, that it was sent? Yeah, so it looks right here. Would you like to mind helping me on E and F on some? Yeah, so do you want me to go? I'm taking 320 next semester. Are you teaching that class? Yeah, I think so. I've already well-versed in Java, and I was in computer science before transferring to you. Oh, that's awesome. Yeah, Alexander, right on, man. That's, yeah, you'll be good to go on that stuff. You're welcome, Tiffany. Just tell me if there's an issue with the grade. Like, I do these concepts a whole ton, and the graders sometimes think that there's not, like, shades of gray. So they'll be like, oh, they didn't say exactly this. And it's like, wow, you know, these things are not 100%. Like, is something an outlier? Is it not an outlier? Daniel, what would you like? Which one would you like to do, Daniel? We can hop to the assignment, or we could do a little bit on the activity, but we will be doing the activity later tonight. Yeah, Alexander, email me or Discord me, and let's get you maybe working on some data camp or something if you want to start practicing some code ahead of time. Download R&R Studio. I can help you out with that. You'll be light years ahead. Daniel, do you wish you had maybe had a little practice in R&R Studio before 320? Well, yes, but no. To anything in statistics. Yeah, but no. Is it an outlier? Kinda. Maybe. Some people might say it is. Some people would say it isn't. No more coffee. No more coffee. Sad times. What is the topic du jour? What shall we do for our topic? Who has a choice of topics? I think Daniel's got the next one. So Daniel, take your pick. Which assignment? Should we do the activity or the assignment? Yeah, exactly. There's a lot to learn, and glad to hear you're learning a lot. That makes me proud right there. Lot to learn. Someone said the courses are very information dense, which I hope is good, right? Hopefully it means you're learning a lot, not that you're just being too much information. Which one shall we do? Activity or assignment? It is Daniel's call. I know you're saying E and F with assignment 5. Yeah, here, I'll send you the Getting Started in R playlist and tell me if you have any issues. So, Stat 201, UTK. I'm looking at the thing of me drinking my coffee. So this will walk you through how to get R. Let's talk about it. Okay. Here is the Getting Started in R playlist I put together. Let's do the assignment on Watch Your Activity Night. Awesome. Let's check it out. E and F for assignment 5. Okay, getting E and F for assignment 5. Dun, 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 dun. Nice piano music. Basically downloaded all the free piano music you could get from YouTube. E and F. Thank you so much, Dan, for swinging by. I get sad. I'm like, where's my 320 students? Assignments E and F for assignment number 5. Some regression. I'll do some parts of this right here. Let's take a look. We got the key, or not the key. We got the everything. Okay, let's check this out. E and F for 320, assignment number 5. So we're actually doing some regression right here, which is what we were doing in 201. So let's go down. Can we jump down to part E? You bet we can. Oh, Daniel, you're doing great, man. You're on the last part of this right here. Okay. Is it gotta go look at the book? Oh, man. What's it say? Part E. It's part E from the book, right? So we gotta go to the book. Okay, wait. Using the autocorrelation. We are going to, in the textbook section 310, part 1, we need to load the NFL data. Let's load in our NFL data. Now, what do we need to do first to get the NFL data? Because I'm going to go here, and you're going to say, it's not loading. Where is it? Where is this located? It's showing where it's located. Part 3 on page 125. Yep, we need to go to the package we can use, or the book. Book is excellent. If you haven't read the book, it's really great read. So we need to go to the reg class. You might not have reg class loaded. You say it doesn't load. Make sure you have reg class loaded. Reg class is the regression class library. It's going to have the NFL data in it. Once again, you can tell if you watch when I write these things in what library something belongs to. If you look right there, that's from the reg class. Yep. So it's going to load in the data right here. And we won't use load. And don't worry, HTT, good answer right there. Load will load in environments. So we can load environments with load. So if we have a .r dat file, we can do the load. This loads data, which is already kind of loaded into R, and these are all data frames I can load right here. We see a lot of the FPP3 probably from time series. That's data sets right there, and there's best GLM. So if I do air quality, I'd load in the air quality data set. So there's the air quality data set from best GLM, and it looks like someone else did it, probably popular data set. Daily air quality from New York? Are they both that? Oh, different one. Huh. Interesting. Fun stuff. Loads in the data. Let's go ahead and grab that assignment sheet. We need to go to modules. And we need to go to, where's our packet? We're going to download the homework packet right here. And the homework packet's going to have the homework. Shocking, right? I love my sound effects. And we're going to go down here to page 128. Here we go. Is it 125? It's 128, you said, right? Double check. Oh, I think you said 125, right? So page 125. Yep. Not 128. Here we go. 125. Part E. Here we are. Obtain a 95% confidence interval for the slope of the regression, predicting wins from EX2. Oh, good stuff right here. So these are, I think this is the only thing I didn't cover. I might even send an announcement about this. I think this is the only thing we didn't do in class because I'm seeing everything, and I was a little worried yesterday that we didn't do like something needed, and this is the thing. So you know what I'm going to do? I'm going to do this one. So I'm just going to straight do this one so people can see how to do it, and so you'll get the answer for this one. So this answer is just going to be straight out there. This one we do know, we can tell the answer to. I'll maybe give some allusion to the answers. But let's go ahead and do this one and just straight give the answer for it. So we must create a confidence interval. Did I show it? I might have shown it. I just have a lot of members of doing it. Okay. So we need to create for E. I could just use this. Boop. A model predicting, let's look at it. A model predicting wins from the fumbles recovered. So we have wins and fumbled recovered. We might be able to copy paste. And let's go here. And what do? We save into the object M a linear model. I'm going to make it bigger so we can see. And we create the formula y tilde x comma data equals. And here's our variables. Wins right there from this. Now that should be spelled correctly, I hope, because it's taken from the book. And we're going to use EX3 NFL. Did it work? It worked. So once again, I'm copying straight from the book because I don't want to type these things out and make errors. If it doesn't work, you probably misspelled them. It's very easy to make a typo and misspell them. Double check your typing, but also do not do the following. Do not do the following. Do not do the following. This will get you the right things right here. If you go to fumbles, and it was it fumbles recovered? There it is down there. Do not use the EX3 NFL before this. This will cause issues with some of the code. If you do it this way, it will create the regression. You could use it to get the variable name spelled properly because you get the autocomplete, but do not write it that way. Y tilde x comma data equals. Y tilde x comma data equals. Y tilde x comma data equals the name of your data frame. This is the format to use if you, it does sound redundant, right? And so make sure you do this format. Don't do it with this format right here with the data frame $. That will create issues. Y tilde x, once again, take a look. Y tilde x comma data equals. We will use this a lot, and it's used in other classes too. Using this format this way does not cause issues. One thing I like to do is I always like to visualize my models to see what's going on. And you can see right here, this model looks pretty flat. Let's go do a summary of the model, just take a look at it. A summary of the model is going to get us the estimate of, oh man, it's going off the screen right there. Let's do it again. Summary of the model is going to get us an estimate of the intercept and an estimate of the slope. Now, what's interesting is the slope is or is not statistically significant. The slope is or is not statistically significant. So the slope is or is not statistically significant. What does that look like? And so good 201, good stuff we were covering this day in 201. The slope is or is not statistically significant. I'm going to answer some big questions right here. The slope is or is not statistically significant because the slope is the x variable. This is the x variable. We don't really care about the intercept. No one cares about your intercept. We only care about the slope right here. And yes, the slope is statistically significant. That's what these stars mean. The stars are actually a way to denote significance. The more stars it has, the cooler it is. I can't even speak today. We don't care about your intercept, though. We only care about the xy relationship. And so when you look at this right here, the slope is statistically significant. Alexander right there, 201, knowledge coming through, 100 points in the chat. And so now what we want to do is we actually want to create a 95% confidence interval for the slope. So here's how to do it. And here's how to do it for the test. If you were to create a confidence interval, when you hear 95, what z-score comes to your mind? When you hear 95, what z-score comes to your mind? If you hear 95, you think of a z-score of what? 68, 95, 99.7. You think of a z-score of what? If you hear of a 95, like a z-score for a 95, you think of what? Good review of 201. 201's getting to hear how all these topics are applied in later statistics. If you hear of 95, you're like, well, that's a z-score of this. 95% of the observations are expected to fall within blank blanks of the mean. Good review. That's a 90% z-score right there. That's a 90%. Great job, Daniel, right there. 1.645 is a 90% z-score. You might know the actual number. 2. Yep. 68, 95, 99.7. So 2, or classically 1.96, or if you want to be like Brian, 1.9599. But 1.96 or 2 is the 95% confidence interval z-score. So watch this. If I were to take my estimate and go plus 2 standard deviations and minus 2 standard deviations, I have just created a confidence interval. And here's a hint for other questions. The standard error is just your what in your estimate. And I think we mentioned this during class, or I'm pretty certain we did. I've just said these things a lot of times, so I'm like, when did I say this last? The standard error is just your what in that estimate. Your standard error is just your what in that estimate. It's the amount of this you have. The standard error is just your what in your estimate for the slope. Like, I think the slope is this, but I could be off by about this amount. So it's becoming a plus or minus down here. We're timesing it by this to create an interval. It's your uncertainty right there, HTT, doing some 474 memory right there, I believe. It's your uncertainty in the estimate of your slope. So you might say, well, that's a lot of work to get your confidence interval. Well, watch this. Confident. Do you have any idea, take a wild guess of what I'm going to put inside of the confident to make a confident for? And it will do a 95% confidence interval by default, but just take a wild guess of what I'm going to put in there to get the confident for. Take a wild guess of what will go inside of this confident formula right here, or function, I should say. Inside of confident, I'm going to say, give me the confidence intervals for what? So you're like, how could I get the confidence intervals? What will I put inside of confident, which gives you confidence intervals? It's model M. And look at this. 0.06, and it's rounded a little bit differently because it's doing it more exact than my estimate calculations. And then 0.247 is more accurately this right here. So this is a way to estimate it because it's basically 2 standard deviations up and basically 2 standard deviations down. And I want to point something out. What do you notice? And this is good conceptual stuff here, so I'm answering all the questions. What do you notice about the confidence interval for this slope? It could be as low as about 0.06. That's not horizontal. Or it could be high as about 0.24. So what do you notice about the confidence interval for this slope right here? The confidence interval for this slope does not include what value, which would indicate no slope, which is the naive model, which means we didn't explain anything. The confidence interval for this slope does not include what value, which is the naive model. So our slope could be as low as 0.06, which doesn't include it. You've seen it right there. So we're saying we do think there is some slope. The slope might be small, but we don't think the slope is equal to 0, which is the naive model. So we have evidence the slope is not equal to 0, hence the slope is statistically significant. So notice how we have a statistically significant slope, and the slope does not include 0. But I'm going to do a trick right here. Let's go here and go attach. I'm going to try to find something. So we're just showing an example right here, and I'm cheating by using attach. Oh, that's even more significant. Now the slope's going to be even less containing 0. Darn it. Give me a not significant variable. God, they're all significant. Oh, we found it. This slope right here is not... So would you have a reason to add a round function? Oh, you could. Yeah, if you just don't... Yeah, great answer right there, HTT. You could if you want to round it. Great answer. This slope is not statistically significant. So what will be included for my estimate of what the true slope might be? The true slope could be what for this line? Because it's not statistically significant. So the true value of the slope, beta 1, remember beta is the true value of the slope could be what? Like I'm saying, well, the slope is not statistically significant, so it's quite possible that the true slope could be equal to what? And then I'll do a confidence roll to show it. This is a totally different model right here where I'm using defensive first downs allowed by penalty to explain the wins, and the slope doesn't look to be statistically significant. So the true slope for this model could be equal to what? Which I can tell by estimating it. Not really anything. The true slope, because it's not statistically significant for this model, might be what? The true slope for this model, because it's not statistically significant, could be what? Since it's not statistically significant, the true slope could be what? So anytime the slope is not statistically significant, we're saying it's possible that the slope is equal to this value. It's possible that the slope is equal to this value. It's possible that the slope is equal to this. If the slope is not statistically significant, well, maybe the slope is actually this. Because maybe the relationship is by random chance. Great job, HTT and Daniel. So it is 0, because if you look at a confidence interval, we're saying that we think the slope is somewhere between negative 0.06 to 0.02. So it goes through 0. Does that make sense right here, Daniel, that the slope is probably some value between there, which contains the value of 0. So I don't think the slope is significant. One, the p-value indicates that, but also the slope is somewhere between these values, and the slope could be 0, which would indicate no xy relationship. Is this conceptually making sense right here, that if you estimate, and that's what the confidence interval is doing here, is estimating what the value of the slope might be. It's saying, well, maybe the slope is somewhere between here and there, because we don't know what the true slope is. We're trying to guess at it right here. Like, here's what we think the slope is. That's our best guess of the slope. And then we have this amount of uncertainty, but so if the confidence interval includes 0, the slope could be exactly. These are what we think the slope could be. Daniel, great answer right there. So since the confidence interval contains 0, which is kind of answering some other questions, right? Then the slope could be 0. And since the slope could be 0, it's not statistically significant. Does that make sense right there, Daniel? So the confidence interval contains 0, so maybe the slope is 0. And if the slope is 0, then there is no relationship. What you can actually do is you can run a code, don't include all these, but you can do possible regressions, which shows you the possible regressions. And you can see right here, wait, so if the confidence interval slope... Okay, so wait, Daniel, rephrase it and I'll review again. I'll rephrase that last question. I'll go into greater detail. This is a confidence interval to estimate the true slope. So that's what that's doing. We thought the slope is negative 0.02, but we think the true slope, like this is saying, well, what is it for all data? It's probably somewhere between negative 0.06 to 0.02. So the true slope goes through 0. Like here's our slope. You see how our slope is negative? That's the red line. But the true slope could be a little more negative, or it could be positive, and thus, I don't know, maybe there is no slope to this line because maybe it's flat. Like it's possible that there is no slope. It's possible that there is no relationship, and that's indicated here and also indicated by it not being statistically significant. Correct. The confidence interval is for the slope, not the x values. This is the relationship that x and y have, not for like the x values, because it is the x variable, but it's the relationship x and y have to each other. So this is estimating that the relationship x and y have might be no relationship because 0 is contained. So it's trying to estimate the slope of this line right here. Like these values right here are saying that the slope could be as much as negative 0.06, or as much as positive 0.02. But since it goes through 0, that is not statistically significant. If we do have one that is statistically significant, like here, let's do the classic one of height and weight. Using height and weight right here, you see it's a much stronger relationship. So if I make my confidence intervals, will this confidence interval include 0 for the slope? So since this is a super statistically significant relationship, will this confidence interval include 0 for the slope, yes or no? So this is super significant. Could the slope be 0? Is it likely the slope is 0? This is super significant. Will a confidence interval to estimate the slope include 0 as a possible value of the slope? Will a confidence interval to estimate the slope include 0 as a possible estimate of the slope? No, it will not. And look down here at the bottom, 0 is not included. You might say, well, that's very small numbers, but the interval is from 0.066 to 0.08. No, because the standard is exactly. The ratio is important too. So the ratio of these, because it's very small numbers, and then the p-value here is significant. And the quickest way, Daniel, great answers right there, Daniel. The quickest way to find out if the confidence interval would contain 0 is if it is statistically significant, it will not contain 0. I'll repeat that. If it is statistically significant, it will not contain 0 for the slope. If it is not statistically significant, it will contain 0. If it is not statistically significant, then the estimate of the slope could be 0. That's saying, well, maybe it is 0 because it's not significant. This model, however, is significant, so the interval does not contain 0 because we don't think that there is no relationship between this data. So if we do the possible regression right here, what are we going to see? The possible regressions by random chance would be here, but here's our slope. So by random chance, we would see these, but does our slope look by random chance, yes or no? These are the slopes. I said something before. That's not from the confidence intervals. These are the slopes by random chance. Here's our slope. Does our slope look to be by random chance? Yeah, thank you so much. Yeah, this is great review, Daniel, and this is great answers for everybody. And this is the conceptual right here. Does our slope look to be by random chance? These are the slopes by random chance. Does our slope look to be by random chance? Here's our slope, and here's the ones exactly. That does not look to be by random chance, but here's our slope, and here's the ones by random chance. Slopes by random chance are going to be close to 0. Look at our slope. Does our slope look to be by random chance now? And this is a different model. This is the model we did earlier that had a high p-value. Does this slope right here look to be by random chance? And there's the p-value. This one looks to be by random chance, and it's likely by random chance. Compare that to a slope that has a low p-value and is very unlikely by... Exactly. This one's unlikely by random chance, and the previous one with the higher p-value is very likely by random chance. Slopes that are flatter, closer to 0, the naive model, are more likely by random chance. And so this is really, Daniel, please ask away. I think we covered anything that we didn't cover fully in class. We did kind of mention these things, but if I don't do something fully, then I'm more than happy to kind of give away the answer in here. Because I don't want people to get stuck on stuff. I want people to pretty much, is the relationship between next year's wins and this year's wins statistically significant? And so if you're going to quote the relevant number, what would you look at to quote the relevant number to see if something is statistically significant? And then we'll talk about this right here. What number would you quote to look at the relationship between something to see? This is not the actual relationship, but what number would you quote right here? I'll let people say in the chat. How would you know if a relationship between two variables is statistically significant in a regression model? It's the same number here. So for the simple regression, you could do either one. This is the significance of the model, the p-value, and specifically the p-value great answer right there, HTT, the p-value of the slope. You want to make sure you get the slope one. Even though these are the same, it'll be the p-value of the slope. The intercept, no one cares about you, intercept. We don't care about you. Now, the next part of that asks, is it relevant? Does it help us make decisions? What two measures for 100 points each, so take a moment, what two measures are used in regression to talk about practical significance? Let me write that question on the screen. Such a great question. What two metrics do we have for practical significance in regression? And there's more. Someone might come in and say MAE, MAPE, all these things. There's a bunch of ones. MASE. But what two metrics do we have in regression to talk about practical significance? See if you can figure this out. Really good question right here. What two measures do we have in regression to talk about practical, not statistical? That's statistical. Maybe I should not make the link. That's statistical. The p-value of the slope, which is the p-value of the model. And if you're wondering, just looking right here, this is the p-value of the slope, which is the p-value of the... Where's that? There it is. Yes, p-value. Good. I thought that was R-squared. What two measures do we have in regression to talk about practical? Like, do I care about this? Do I care about this? Correctly does. Yep, it does depend on. And what two measures could you quote? You want to quote some values right here. What two metrics do you have to quote? Well, so you want to make sure you quote some metrics and talk about them. So the big thing that the graders will be looking for right here, so we're going to interpret this one. The big things that they'll be looking for is you quoting metrics and talking about those metrics, because it's basically asking you to quote at least one of these two metrics. So look on the screen right here and see if you see any metrics on the screen that we could use for practical significance. So remember, p-value is statistical. So that's not practical. That's just going to give leeway. We need to first see statistical significance. So this is statistically significant, so it might be practically significant. So then what do we have for practical? Two metrics to look at. What is one of the two metrics which would tell us, do I care about this? What can we then interpret? 201 maybe knows. I bet 201's got some... Maybe 201 can help out a little bit here. Let's look at a little cheat sheet right now. Will help on the 201 cheat sheet right there. Any ideas what we could talk about? And actually, it's got the explanation. What is a practical significance? 320, don't look at that. Don't look at that. That's a bad way. 201 does it wrong. Sorry, 201. What could we look at right here? A measure of practical significance we could use is what? Oh, no. A little more chill music. Was one of the two metrics for practical significance that we can analyze and talk about and explain. Be like, well, you know, it does this, and so I think that's significant, practically speaking. One of the two metrics will be... Say it here in a second. It's good to memorize this. Be like, okay, Daniel, you got it, man. You got it. R squared. R squared right here is one of the two metrics for practical significance. So we actually have the straight interpretation right here. So actually, let's do a little 320 right here. Practical significance are R squared right here. So we have 36.13% of the variation in somebody's height. I was explaining height right here. You can see its height is explained by the variation in their weight. So we're using the y variable height and the x variable weight. So 36.13% of the variation in somebody's height is explained by the variation in their weight. That's over a third. Over a third of the variation in your height is explained by your weight. That seems like a large portion to me. Like if I know how much somebody weighs, that gets me over a third of the way to understanding how tall they are. Now, I wouldn't know for certain how tall they are, but it's a lot of good information. So I think this is very practically significant. Look at the argument I just made right there, trying to tell somebody why I care. The last thing we have right here is RMSE, which is root mean square error, which we did cover. RMSE is a measure of practical significance telling us the typical miss the model makes. So let's go right here. The model typically misses Y by, I knew I had that on, by RMSE units of Y. So we typically miss by RMSE units of Y. Make sure it's in the units of Y. It's not a percentage. If you mix up the X and the Y and the R squared, it does. Yeah, that would be wrong. Because remember, the X is explaining. So blank percent of the variation in Y is explained. To make that very clear right here, it would be wrong. It does technically work. But remember, we are trying to say that the model, go away, that's how I want to spell it, is explained by the X variable. So it still works mathematically, but analytically, it's wrong to say we're trying to explain X using Y, because the Y variable is what we want to understand. So we're explaining the variation in the Y via the X variable. So the X is doing the explaining of Y. So you could reverse it and say, my X variable gets me 36.13% of the way to understanding Y, or 36.13% of the information in Y is explained by X. There's a lot of ways to talk about it. I think of the assignment probably if you said knowing X gets, 100 points right there, Daniel. Yep, that's perfectly fine. It still says that you're using X to understand Y, which is in the notes too. So there are other ways of saying it. I like to use this structure. It's the structure I've used for the longest time. Petrie uses a slightly different structure, but it's just like you said, it's like you have this variable. How far does it get you? So we're trying to explain variation in Y. So this percent of the variation in Y, you could say blank percent of the variation in Y is obtained by knowing X, or the variation in X. There's other ways to change it up, but I try to keep everyone to like a similar structure. One, so the graders don't grade things incorrectly, and two, because I used to not give people fill in the blank stuff, and some of the answers would be pretty crazy. But there are ways to go outside the structure and give great answers. When you see the RMSE right here, take a shot at the RMSE. Use my model right here and interpret that RMSE. What do we have for an RMSE interpretation right here? So the model typically misses what by this many units of Y. So look at the RMSE right here. The RMSE is the root mean squared error, which is the residual standard error. So we should put right here a note and help people out here that RMSE, I thought I told you to be wrong button. RMSE is residual standard error. The RMSE is the residual standard error. It's definitely not correlation today. RMSE is the residual standard error, and also R squared is not correlation. I should put this below here as a note. RMSE is the residual standard error, and R squared is not correlation. It's not correlation. Do not interpret it like correlation. I mean, you can find correlation with it, but it's not correlation. It's an aggregate of correlation in some ways. It's being used in a lot of different problems, more advanced topics. So when we talk about the RMSE right here, we need to look at where the residual standard error is, and that means your uncertainty in the residuals. It's about how far the points are away from the line. That's what a residual is. Remember, residual is the distance points are away from the line. So it's going to give us an estimate of the typical miss the model makes. So the model typically misses height by about 3.554 inches. So make sure it's not a percent, it's not a factor. And one of the great things you can do is you can actually go look at this. Let's go look at our model, remember 3.554. Visualize model M, and I want you to take a look that if you were to go here and take this and draw lines on it, if you were to go up about 3.5 units, which that looks to be, you get that a lot of the data is within here. The typical miss, not every point, but like what we miss by on average. Like some things are within this, some things are without this, but this is about how much we miss by on average. Does that make sense with the RMSE is, David, right there? It's how much we standardly miss by this. Like we miss by about this much on average. So is it a lot to mispredict someone's height by about 3.5 inches? I mean, that's a pretty big miss. So maybe I'm a little more worried about the practical significance of this. It's not really significant. Well, not like amazingly practically significant, but you know, if we predict them to be about, it's not, I don't know. That's a little less sounding amazing to me. How about if we want to predict the wins a team will have, more like your assignment, right? So if you're looking at predicting the wins a team will have next year, and this is major hints for your assignment, I want you to look at this one right here. And when I predict next year's wins for a football team, I'm typically off by about 3 wins. So predicting the wins for next year, predicting the wins, or we could do next year's wins. I got that in here. I have the... So when I predict next year's wins with this model, I'm typically off by 3.128. First off, my model is not statistically significant, so it can't be practically significant. So there is no possibility for practically significance because we do not have statistical significance here. But if I told you, I think your team's going to win 9 games next year, but they could win as many as 12 or as few as 6, like I'm typically off by about 3 wins. You see a lot of teams are within about 3 wins right here of my prediction. Sometimes it's a little bit more, sometimes it's a little bit less. Things are closer, but is being off by about 3 wins, plus or minus, on a team's wins, is that a big miss for football teams? Like if I predict 9 wins, probably you're going to get somewhere between 6 to 12 wins. Probably. You might get outside of that. That's what this value means, is like, I think your team's going to get 9 wins, but maybe somewhere between 6 to 12, because I really have some uncertainty in this prediction. How good does this prediction sound to you? 12 wins, your team's doing pretty good. 6 wins, your team's not doing pretty good. Difference between playoffs and no playoffs. So you'd say that's a pretty big window. If I tell you the Titans are going to get between 6 to 12 wins this year, you'd be like, probably that's a lot of the teams. The Patriots are going to get between 6 to 12 wins this year. You'd say, yeah, that's what goes on. So with this right here, I would not say that this is very practically significant. First off, it can't be practically significant because it's not statistically significant. But second off, just interpreting the residual standard error, the RMSE, even if we were wondering, it doesn't sound very practically significant. So you have to quote the numbers. Daniel, how are you doing? Have you gotten this assignment completed? Let me know if you have any questions on anything right now. Your call, Daniel. What else should we talk about with this? Really good talk on the 320 assignment. Hoping people get the whole thing completed. Last part might be a little challenging right here, but I definitely did. We got it in the video, so we should be good. How are we looking on that assignment? Good stuff right here. Simple linear regression. Building that line right here. And I love how we can do all these things. I wonder if what? It's gonna be interesting. Let me see how it looks. Oh, they've already done it. Can you rephrase A on the assignment? I was kind of confused. Oh, let's do A next. Yep. I'm going to do something real quick right here, and then we'll do A. Is this safe to go to? Let me look at this person's thing that they're posting again. I want to read it more real quick, and then we'll check out A. What's on the crayon? Okay, crayon, you better not do me wrong here. Looking good. Wait, which number is it? Let's give updates. Crayon, you better not do me wrong. Take a look at number 8 here in a second. GG. Okay. Library. Got it. Okay, cool. And what is the name of their thing, their function again? Let's see what I got. Why is it not on the crayon server yet? ggplot. What? There's the summary. ggpredict. And let's see. They have this fit. Okay. So they have the model. And it works. And there we... Oh my gosh. No way. I don't even know how to do this stuff. I'd have to look into this code. Wow. Oh, but your screen size is a little bit crazy here. It's showing the equation of the line. Oh, but it doesn't put in the variable names. Oh, come on. That is cool. What do you think of this, Daniel, right here? I'm checking out a new package, which, and then we'll go look at A, but this you can hover over and you can actually see the values. A lot of text. We'll go and look at our height weight one again so we don't have so much text on the screen, and then we'll rerun the ggpredict on it. And now we can get a model right here, and you can actually see the height and weight of the individual pretty clear and easily. So you can just hover over a person and see that this is point number 662 with a weight of 270 and a height of 60. And you can even go to the model right here and get the equation for the model by looking at it. I wish it was maybe a little bit darker text. The alpha on that could be changed. I don't know. I might go there and look at it, but I don't know why it's highlighting that one point on it. That's a little weird right there. But that's really neat. You can download it. Download as a PNG, so you can save it as a graphic file. That didn't do anything right there. Check it out. Zoom in. Oh, I don't know. Maybe, oh my gosh, what have I done? Craziness. Neat stuff. And then, well, that's really cool. Oh, there we go. You can zoom in. Well, then how you... Having too much fun right here. Remake the graphic. Let me look at one more thing right here. This is pretty new, it looks like. When did this come out? This came out at the end of last year. This is by Kin Wong Moon. Great stuff right here in this package. And then they're doing extra things right here. They got multiple regression. Great stuff. And yeah, that's really neat. These are super clue. And logistic. Oh my God, that's so cool. Okay, let's take a look at number A right here. But this is a really neat way to do your regressions. Hadn't seen it. And let me try one last thing on this. If they've done this properly, then we should be able to do... My ggplot's not loaded? How could ggplot not be loaded? And there's ggtitle. It doesn't like it. Okay, so it's not... The ggpredict is not working with that. So yeah. Well, that's interesting. Let's get the height, weight. We can't add the title. Geom title. Let me try that. Last thing right here. Does it work with the geom title? Ooh, whatever. What's going on right here? What have I done to myself? Geom title. Geom underscore title. Geom title. Well, can't find it. Plus title. Let's take a look at number A here. I'm having too much fun with this. Can't find the function to do what I want. Let's head back. So let's take a look at number A on BAS 474 and take a look at it right here. Number A, as Brian looks at new packages and new ways to plot stuff. The conditions again. So let's take a look at the conditions right here and talk about them and what conditions there are for regression. I should have some notes on that from yesterday. Okay, here we go. Talking about the conditions for regression and why maybe something violates the conditions. Let's take a look. Series number A for 320. And we have three conditions. The three conditions are that the residuals are what? I need your help right here. Tell me that the residuals should look what? We were just talking about this in 201. But the residuals should look what to start? Residuals should look what to start? Residuals should look what to start? Residuals should have a what pattern? Residuals should have a what pattern? What pattern should residuals have? What does that mean? Residuals should have this pattern. So it's kind of like we're going to fit to the data things like this. We're going to fit, we'll take all these residuals right here and we'll look at, kind of if we take a slice of time, it should look like this. Now this one violates a condition for certain. Not quite cylinder. This means normally distributed. This is what, now this one does have a cylinder pattern, which is not good. So we don't want it to have that sort of pattern. We do want a normal distribution to the residuals. So if you were to take all these values of the residuals, watch this. We can go to our regression, and we have a regression on the screen right here. And we can go to residuals, and with residuals, we can take the residuals of our regression, and we can put them in a histogram. And there's a histogram of our residuals. Does it look normal? It's got a little bit of skew, right? So let's investigate skew. Does it have skew? Oh, can't find function QQ. Did you take away my QQ? Because I think it restarted. So here we are. It does have some skew to it. So remember the QQ plot or normal quantile plot is going to show that we have some sort of skew on the side right here. These values down here are a little bit skewed. So is this normal? I don't think it's quite normal. The second condition is that it has a mean of 0. Now this is the confusing one, but the line itself right here is where the mean of the points are. So does this have a mean of 0? Does the line go through the data? This is actually the linear condition. Is the plot below linear, yes or no? Is the plot below linear? So it to be normal. Is the plot below linear, yes or no? Be careful, don't overthink it. Is the plot below linear? Does the line go through the middle of the data? Kind of QQ straight enough. Does the line go through the middle of that data? Like, is the line kind of the average of the data at all points, saying that the average residual would be 0? So it is linear. Yep. And things that would violate that condition we have highlighted right there would be if we had a line like this and the data went around it, and it would violate the not linear, because now the average residual is not 0 at all points. So this would violate the linear condition right there. Linear. And last but not least, we have a 201 condition we talked about today, which is this. What do we call this in 201 right here? There is a huge violation on this. And this is one of our favorite terms in 320 to talk about. But there's a huge violation right up here on this one. Those colors do not match what we're talking about. So this is the good version of it. And the bottom has the bad version of it. So we want a constant spread to the data. That says one value well describes the spread of the residuals. So this does not have a constant spread at all points. So what do we call this in 201 terms or 320 terms? What do we say here that there is not a constant spread to the data? How would we talk about this and say that there's an issue? How would we talk about this? How would we say this? I have an idea for a visualization I want to make to explain the answer to the question. Heteroscedastic. Yep, this bottom one is heteroscedastic. This top one is homoscedastic. Same spread on the top graphic, differing spread on the bottom graphic. 201 knows this as the plot thickening. We don't want plot thickening. We want the plot to not thicken. This has same thickness throughout. This has differing thickness, which is a bad thing. We do not want the heteroscedastic. Great job right there, HGT. Good practice. And so one thing I want to do right here is I want to make this model. Let's go look at the model we're supposed to make and see what the data says. So we can predict winds. Oh yeah. So when we're predicting winds, let's make a model predicting winds. So let's go here. We've got the data loaded up. We went to reg class. I actually need to reload reg class. Data EX3NFL. And then we're going to predict winds. So let's go to M, save into LM. Winds. I don't have my autocomplete anymore for that. And let's go here to, I'm going to cheat and go to the attach function, which attaches the data frame to the global environment to let me type in vectors like EX21 passer rating and data equals EX3NFL. I do want to point out again that this is Y tilde X comma data equals data frame. That's a Y. So make sure you do this from here. You should be like butter toast. Nice to remember that HT right there, HGT from last semester, I think. Nice quotes from Gold Score right there. When we look at the residuals right here, I want you to look at the residuals. The residuals are going to be rather interesting because with the residuals, we are trying to predict things that are whole numbers right here. We are trying to predict a Y value. Let me see right here. Technically predicting the winds, which can range, is not a task for which regression because the number of winds is an integer amount. Exactly right here. So when we're predicting an integer amount, we'll generally have misses that are kind of consistent right here. And also we're predicting by passer rating. Let me go to next year's winds. And I want you to look at the residuals. There's going to be a lot of repeat residuals, or I believe there should be. Let's take a look right here. And let's do a table of the residuals. And we do have a lot of repeat residuals, and these are very decimal place accurate. So it's kind of weird that we're getting repeat numbers. And let's talk about what's going on right here, like conceptually what's going on. Like this residual occurred 10 times. I want you to think about this for a moment right here. This number, which should be by random chance, occurred 10 times. That to that decimal place accurate. When we're using integer-based numbers, we're limiting the possibilities. And I wonder if, I want to see here, ggplot.plot. Can I get a dot plot? Can I get a dot plot today? Oh, I just want... Yeah, this might actually work. I just want one dot plot, though, not a bunch of dot plots. They're doing a bunch of dot plots. I just want one. Beautiful dot plots, though. Ooh, Tidyverse dot plots. Oh, here it is. Here it is. I found it. Got it. Okay. Taking the NPT cars. Okay. This is getting to the answer and why we can't do this. So I'm going to make a dot plot and see how it looks. So here we are with the model, and I need to take my residuals. We're going to make a data frame. This is a lot of extra work just to show the concept. Data frame of residual RSE equals residuals of model M. And so this will be our data frame. The aesthetic will be the residuals, which are SE. And we should get the dot plot right here. So the issue becomes with this dot... Whoa, what you doing, R? So with this dot plot right here, I don't like how it changed the perspective. I want to make it a little bit bigger. Let's plus that to that. With this dot plot, there's actually limited values. I wonder if I can change the aesthetic of it a little bit here. With the dot plot, we're actually limited. I'm going to need to look at method bin width. Bin width, back to 201 again. So bin width equals 0.1. I like it. If you look at what's going on right here, we are getting little gaps. And this is where we have the repeat values, where we have a bunch of values that are repeated multiple times. Oh, can we change the height of it? Oh, watch this. Oh. Plotly. ggplot. Oh. Could not. Oh, because dplyr. Okay. And so now we should get it. Awesome. Zoom in on this here. I wanted to zoom in. I don't like how I made them all dim. That shows it. I don't know why the alpha is so low on that. But this concept is right here, Daniel, and hopefully I can explain it and make sense of this. Take a look at how there's gaps. If you look closely at this, you can see that there's gaps. I'm going to zoom in on this and try to get it so you can see it. But there's gaps in the data. There's gaps between these. And if these are completely random right here, we should not be seeing the gaps. Because when you sample from a random normal, if you're using integer values, and actually notice how there's this nice even spacing to them. If you look at the spacing on these, you'll notice it's almost a consistent pattern on the breaks between the numbers, which that's not random. This is getting to the meat of the answer right here. Notice how these have the same even, it's so hard to see those points, but notice how the spacing between these is more even right here. And that's because what we're seeing with this is that we are building things off of integer values. Yep. And so the reason is because there's only so many values that we're using to predict on, so we can only miss by certain values each time, and that is creating a pattern. How should a residual plot look? And this literally goes back to 201. Since integer values have a pattern, residual plots should not have a pattern. A residual plot, literally covered today in 201, should show what? What should a residual plot show? What should a residual plot show? That's not what it's on chapter 7. Where's our residual plot? What should a residual plot show? What should a residual plot show? A residual plot should show what? When you look at a residual plot, it should show what? Nothing interesting. When you look at your residuals, there should be random variation. And since the y has a pattern, this is getting to the meat of the answer right here. Since integer is a pattern, does it make sense? Why is integer a pattern? Here, I'll tell you. 1, 2, 3, 4, 5, 6. Okay, what's the next number? Just tell me. Do you see the pattern? 1, 2, 3, 4, 5, 6. What's the pattern? Catch the pattern and be like, oh, well, the next number is this because it's a pattern. It's an integer pattern. And if we have this integer pattern, it'll create an integer pattern in the residuals, and then they can't be randomly normally distributed. That's kind of the meaning of the answer. HTT right there, catching the pattern, some 50 points right there. So it's a little bit more advanced way to say we want these things not just to be normally distributed, but we want them to be random normal distribution. So that's what it means. The capital N right there is a random normal. I lost it. The capital N right here is random normal. So your integers are not going to be randomly normally distributed when the y value has a pattern, because that's going to create a pattern in your residuals from the integer pattern. Is it a big deal? Nothing's perfect. Not even statistics. So we say, yeah, that's bad, but just move on. Yeah. Does that make sense, Daniel, for the how to talk about this? And we're talking about these conditions right here. Are they randomly normally distributed, which means they would follow a random normal distribution at all points? Like you should see 68% within here, 95% within here, 99.7 within 3 standard residual standard errors or standard deviations outside of it. But the big problem on this one is going to be the differing spread. We do not see a same thickness throughout. We also want to see that the line is the mean of the observations at all points, which we do see for this data right here. So are these random normal distributed? Probably pretty close to. I don't know, maybe not exactly, but the big problem here with this one is the differing of spread. But an integer pattern in the y will create something like the integer pattern. The quickest way to see it, like the way I did it right here, is think about this. These are I found all the residuals, and when you look at this right here, this number down to that many decimals occurred 10 times. It's this number over here. I'll zoom in on it. I have to vanish from here. But this number right here occurred 10 times. See how it's right before 4? That number occurred 10 times. This number right here occurred 8 times. There's no numbers between them. There's no numbers between these two numbers. This one occurred 10 times. This one occurred 8 times. Does that sound random? Does it sound random that this number to this many decimal places would occur 10 times by random chance? Like if I go and generate a random number, if I go random number, it's hard to make that many decimals. Random normal number with a mean of 3 and a standard deviation of 1, or sorry, I need to generate one number with a mean of 3 and a standard deviation of 1. That's the random number I generate. And if I generate random numbers right here, what's the probability of getting that number? It's right behind me here, 10 times. And then the number next to it was generated 8 times randomly. Does that really sound random to you? Does that really sound random? Like, random right there. Is that random? Is that random right there? So the visualization is a little bit weird to look at, but would it be random to generate? Because the residuals should be random. So should we be getting a number like this 10 times? Should we get one residual 10 times down to that many decimals? If residuals are random, then the likelihood of getting this right here 10 times in a row is virtually impossible. Does that make sense theoretically right here? Because of the integer pattern, we are seeing patterns in our residuals, making certain residuals appear more often because they're based on the pattern in the y value. This is more of a direct answer to the question right now. But it's evidence right here via one of the residuals down to 12 decimals or so occurring 10 times. We have other residuals. These are the values of the residuals. Like when you look at the model, we got 10, it's like having 10 identical children. And if you look at the model, that residual of 3.5, we could kind of find something that looks like that. That's going to, you see the pattern in it right here. We did last video, I think, Chloe. Great question, Chloe. I think we did in the last video. Check out, they're all labeled now. Yes, went through and labeled all the videos last night. So you should see some Viz 5, and there's the Viz 5 playlist. So check out the videos and tell me if you can't find it. I'll send it to you. That residual must be occurring on one of these right here. But do you see how there's a pattern? You can see how there's a pattern that's going to cause repeat values, repeat residuals. And so because of this, you're seeing one of these with the repeat values is going to cause it where there could be y's with repeated values right here just because they have the same, and then they're going to get the same prediction, and then we're going to see the same repeat residual a bunch of times. Something with a residual of about 3, which has to be one of these positive ones, which is going to be, maybe it's in here or so, because there'd have to be like 5 and predicted to be about 6 or 7 and actually 9 or 10. But does that make sense? Like, the integer values limit the y, and thus we have a pattern in the y that is going to be prevalent through multiple observations. And then we're going to see repeat values of residuals because of this pattern. And those residuals are not random. Like, it's not random to get this number 10 times. Like that, or it's possible random, but unlikely random. How are you doing on this one concept? This is a huge conceptual question. Like, this is all statistical theory, which is good, I like statistical theory. But this is major statistical theory. Like, on why it's not like you can't do it, but it's kind of like, it's a little like, well, it doesn't perfectly follow a random normal pattern because we have repeat values that wouldn't occur randomly. And this is due to the integer pattern in the y variable, creating a pattern that would create patterns in residuals. The pattern in the y goes through to the residuals. Patterns in y carries through to patterns in residuals, because how do you get a residual? Last thing to mention right here. How do we get a residual? And we're talking 201 right here. So think about this. Here's the easiest conceptual way to understand it. You ready, Daniel? What is part of the formula for finding a residual? So what is part of the formula? So I'm highlighting it right here. What is part of the formula for finding a residual? Part of the formula for finding a residual is what? And remember, this has a pattern. We're saying this has a pattern, and it's part of the formula for finding the residual. So what is in the formula to find a residual? Like, we have to use it to find a residual. The y value. So if the y value has a pattern, and then we're using it to find residuals, that will create patterns in residuals, and then the residuals won't be completely random normal. So the normal is not just normal distributed, but means random normal. So because y has a pattern, the residual is an aggregate of the y, and thus the pattern in the y will create a pattern in the residual, not allowing it to follow the condition that the residuals must be normally, and by normal we mean random normal distributed. The mean of 0 could still exist, the line could go through the data, and there could be constant spread. But the big problem we're going to see is right here, because if there's a pattern in the y, then we'll see a pattern in the residuals because the residual is an aggregate. That's probably one of the easier conceptual ways to understand it right there via the formula showing it. How are you doing, Daniel? Does this make sense? It's a good conceptual one. We spent a lot of time talking about it, but it's we did some kind of cool, R stuff. You guys know I love programming R. I think that's got it. I need to grab some food real quick. Send the announcement for class. Class in 20 minutes. What? I got back. Oh, yeah, it came back. It's still here. Open up a new sheet. Oh, thank you, Microsoft Word. Delete. I can't add it back now. Why'd I do that? Microsoft Word. Awesome stuff there, Daniel. Great job. We'll start at 100 points to the chat. I'll be back. See everybody after break, or see you for the activity tonight. I'm going to go grab some food, and we'll be teaching class here soon. Bye for now, everyone. Bye. Almost class time.